Hi, I'm Alexander Chen.
And I'm Stephen Fazio. We're team byoLOGIC, working with the self-titrating bacterial protease activated prodrug invented by Brandon Holt and Dr. Gabriel Kwong. We're going to discuss a solution to what the World Health Organization recognizes as a top 10 public health threat: antibiotic-resistant microbes. The problem with antibiotics is that the bacteria they're meant to kill adapt to them over time. Without an effective treatment, our immune system is left as the last line of defense. That's why out of 2.8 million annual cases in the US, 35,000 end in death, costing the US more than $4.6 billion each year. One particular antibiotic-resistant microbe that the CDC recognizes as a serious threat is methicillin-resistant Staphylococcus aureus, or MRSA. Just in 2017, it affected over 300,000 hospitalized patients and caused over 10,000 deaths. Because it can't be treated with antibiotics, MRSA is much more deadly than regular staph infections, killing up to half of patients with a septic infection. MRSA is most often contracted at the hospital by patients that have undergone surgery. In order to combat this problem of antibiotic-resistant bacteria, there is a new case of antibiotics being studied known as antimicrobial peptides, or AMPs. They are small peptides or proteins that are naturally found in the immune system of all living organisms and have a different mechanism of killing bacteria compared to traditional antibiotics.
With this in mind, it is now important to understand the design factors for new antibiotics. For our AMP-based antibiotic, there are three main factors. The first factor is drug dose amount, which is intuitive. If the dose is too low, it won't kill all the bacteria. If the dose is too high, you risk poisoning the person. The second is the drug exposure time. Typically, if you're prescribed antibiotics, you will take them for about 2 weeks, and your symptoms may leave after the first week, and so this extra time is meant to eliminate all residual bacteria. The third factor is based on the AMP type. Because there are hundreds of different AMPs to choose from, with a variety of properties and reactions, you need to choose the right one. So from these factors, there are two general problems. The first is that the infection treatment is a dynamic and ever-changing process that requires different doses at different bacteria concentrations. The other problem is that AMPs by themselves have low stability in the body and can be toxic to human cells at high concentrations. So with all these problems in mind, here's where the patent comes in. First, I need to define a prodrug, and it is a drug that remains inactive until a body function or metabolic pathway activates it. In the patent system, the AMP is matched with a complement polymer that is oppositely charged, and they're connected with a lock. If the blue paper is the AMP and the red paper is the complement, the black paper would be the bacterial protease cleavable crosslinker, or lock. The only key to this lock would be the specific protease found on the bacteria. This is advantageous because the bacterial protease key readily interacts with the lock, which frees the AMP that ultimately destroys the bacteria. This simplifies the solution to the previous problems because the AMP would be stable and non-toxic when connected to the complement and lock. Also, it is self-titrating, which means that the dose is controlled by the concentration of bacteria that the AMP is exposed to, and thus the right dose will be delivered every time. In order to develop a single drug, we need to go through a process of proper testing and clinical trials, which takes up to 10 years and billions of dollars. And this is why we decided upon frulamycin B, an AMP that has been well studied and kills MRSA by disrupting the cell wall. Frulamycin B has already gone through clinical trials, but failed in phase 1 because the human body does not react well to the exposure of the AMP in its active native state. And so here's where the patent's complement and lock method is meant to keep the AMP inactive until exposure to bacteria. So our product idea would be the complement and lock system implemented onto frulamycin B. This would streamline our process since we already have a defined system to create the AMP and purify it. Our job would be to incorporate the patent complement and lock method and begin benchtop tests on drug efficacy.
A frulamycin B implementation of Brandon Holt and Dr. Gabriel Kwong's system would mean the development of a new class of prodrug. A prodrug that only acts on MRSA. A prodrug that will be cheaper to develop. A prodrug that will lower infection mortality. We hope you find this the biological solution Thank you.